self-energy diagram, which looks like this. Okay, welcome to our last week of quantum field theory in this semester. We are currently discussing one-loop corrections after the semester on free field quantization, interactions, Feynman rules, and three-level Feynman diagrams in QED. And the single one-loop diagram that we consider here is the photon vacuum polarization, or the photon self-energy diagram, which looks like this. We have a photon and a one-particle irreducible diagram consisting of a fermion loop. And we gave it a name, minus I sigma mu nu of Q, and we analyzed the water identity that we get such a prefactor here and can extract the vacuum polarization. And here are the Feynman rules that we got for this quantity, and today we want to compute this photon vacuum polarization in so-called dimensional regularization. So as you might know, these one-loop diagrams and loop diagrams in general are afflicted by a problem, namely there are so-called divergences in the calculation which need to be treated, and there is a theory associated to this, namely the theory of regularization and renormalization, and so therefore this is what we need to introduce today, and only after that we can actually calculate and interpret the vacuum polarization. So we will begin now by briefly explaining the basic idea of renormalization theory, and we do not need to do very much. There is of course a vast array of theorems and so on associated with it, but in order to understand the calculation we can do it actually in a quite simple way. So let us begin. With the basic idea of renormalization. So I already mentioned it. Sorry, I think I need to close this here. The basic idea, as already mentioned, is the following, namely our quantum field theory is actually a limit of a class of theories which depend on a so-called regularization parameter epsilon, and so we have a certain set or family of theories for different values of epsilon, and this epsilon is called a regularization parameter. So for each epsilon there is a theory defined, and the Feynman diagrams, Feynman rules are defined for each epsilon. And then the actual quantum field theory is the limit of that family of theories where epsilon goes to zero. And that limit should be taken in such a way that two criteria are satisfied, namely on the one hand all observables are finite, of course, and that the limiting theory is actually sensible in physics terms. That means it must satisfy certain physical criteria. Physical postulates are satisfied, and what are important postulates? That would be, for example, causality, unitarity of time evolution. So unitarity of time evolution corresponds, for example, to the unitarity of the S matrix, which we have also discussed in the context of gauge theories. And there we have written down a relationship which must hold, and we checked it at lowest order. And there the problem was these negative norm states. But you can apply similar arguments such that at one loop level also the S matrix should be unitary, and this constrains the limit and the limiting theories that you want to obtain. Similarly, causality means that operators at space-like distances should commute, as at least if they correspond to observables, because observables at space-like distances cannot influence each other. And so these are properties which must hold in the final limiting theory, and maybe it's easiest in lowest order. And there the problem was these negative norm states, but you can apply similar arguments such that at one loop level also the S matrix should be unitary, and this constrains the limit and the limiting theories that you want to obtain. Similarly, causality means that operators at space-like distances should commute, as at least if they correspond to observables, because observables at space-like distances cannot influence each other. And so these are properties which must hold in the final limiting theory, and maybe it's easiest if you implement.
طبعا ربما سمعتم قوله observable distances يعني affect each other. هو طبعا هذا بلغة أخرى أنه الملاحظ أيضا يؤثر على هو طبعا ساق بطريقة أخرى، لكن ما أقوله هو أن الملاحظ أيضا يؤثر على النتيجة، يعني يؤثر على النتيجة من خلال ملاحظته، من خلال وجوده هو ومكانه هو. ربما سنستكشف ذلك في هذه الحلقة، وما سيقوله هو عن observable. أنت بس فقط عليك أن تحول كلمة observable إلى الملاحظ، يعني الملاحظ من أنت، أبعادك أنت وليس الأوبريتور. طبعا الأوبريتور يعتبر ملاحظ أيضا، لأن أنت بتقيس الأوبريتور، هذا الأوبريتور بتقيسه، لكن كل ما يقوله هو عن هذه الجزئية تخيل نفسك أنت المقصود وأبعادك أنت هي المقصودة. أبعادك ضخمة بالنسبة للبروتون، وإذا صغرت أبعادك فإنك ستلاحظ أشياء أخرى فيزياء مختلفة عن الفيزياء التي نراها نحن. طيب تعالوا نواصل.
Them for any epsilon, but the main thing is that the final theory that comes out of this limiting procedure has these properties. And so then for each epsilon you might get a finite Feynman diagram result and finite such loop integrals, but for epsilon going to zero, certain quantities, certain building blocks, certain expressions might diverge, but observables must come out finite, and these finite observables must be in agreement with those postulates. That is the basic simple idea that we must implement. And so let me sketch how this idea can be realized in practice for the example of QED. So in QED we start our calculations from the Lagrangian, and all the Feynman rules, Feynman diagrams, they come from the Lagrangian, and therefore each formula that we write down in QED comes from the QED Lagrangian, which in particular contains two parameters E and M. Therefore every formula in QED that you write down is somehow a function of E and M. That is the point. And so everything that you calculate will be a function of those two parameters, E and M, which are also called input parameters. And so then, as a sketch, you can calculate everything you want. For example, here, observable sigma 1, sigma stands for an observable that can also be measured experimentally. The second observable, like for example, here E plus E minus, 2 mu plus mu minus at low energies, E plus E minus, 2 mu plus mu minus. At high energies or at different angles, theta equals 0, theta equal pi over 2, and so on. So you have many, many things that you can measure. Each quantity for each energy, for each angle corresponds to a different observable. there are further observables, of course, let's say, for example, G minus 2 of the muon, or the hydrogen spectrum. All of those quantities are observables, and you might want to calculate all of the predictions for all of these observables in QED, which means, mathematically speaking, for each of those quantities you will derive a formula, and each formula will depend on two things, namely E and M. That is always the structure. Now I have to go on here below on the lower blackboard. So what is now the discovery, and that is just a fact of life, is that those relationships here between the fundamental QED Lagrangian and its parameters E and M and the observables that you predict, this relationship is divergent. So if you look at the calculated formula, then that formula will diverge for epsilon going to 0. So it might contain 1 over epsilon. So these relationships here they are divergent, for example, like 1 over epsilon. And now, of course, historically, and maybe even now, you might think this is a disaster because it means that our predictions are meaningless, our predictions are infinite. But there is a very simple solution. You can simply say, actually, we know for sure that those here, those are observables. Therefore, they must be finite. If you accept that any observable must be finite, then the conclusion goes in the other direction, namely the conclusion, if you have a finite outcome and a divergent relationship, it simply means the starting point is divergent. And so you can now invert the relationship. For example, you might simply say, I calculate, I use the relationship in order to compute E and M from the measured sigma 1 and sigma 2, and then I will get a divergent result for E and M. And that is not a problem as long as we accept that E and M are not observables. Nobody has ever stated or claimed that this E and M is an observable. And so therefore what we simply need to conclude is that this here are divergent quantities. So the Lagrangian is not finite in the limit epsilon going to 0, and those parameters E and M, they are also maybe not finite in the limit of epsilon going to 0. So for example, E and M are divergent functions of sigma 1 and sigma 2 by simply inverting the corresponding relationship. And in the theory of renormalization, we give a name to such objects, these divergent original fundamental parameters in the Lagrangian. They are called now bare parameters. So they are not observable by themselves. They are just formal input parameters which we use to parameterize our predictions, but they are themselves not observable, and they become meaningless in the limit epsilon going to 0. And the hope is now, which is a non-trivial hope, but we can hope that if we do that, if we use, for example, the first two relations, sigma 1, sigma 2, we take them as finite numbers from experiment, we invert these relationships, compute the divergent E and M from it, and then we predict all the other observables as a function of those divergent parameters, that then the divergences cancel. And so we can ultimately predict sigma 3, sigma 4, and so on as a function of sigma 1 and sigma 2 by just eliminating those divergent quantities, which would then become intermediate building blocks which are actually not observable. So ultimately we can predict everything as a function of two observables, And in those predictions, maybe, hopefully, the divergences just drop out. And we get a finite prediction of all the other observables as a function of the first two. That is a hope.
طبعا الكلام ده له تفسير واحد، هو أن الفضاء موحد. كلامه هذا يعني أن الفضاء موحد، وبما أن الفضاء موحد فإنك يمكن أن تبني على أي تجربة سابقة لتجربتك أنت التي تراها أنها يعني أعطت نتائج غير مرضية أو نتائج غريبة. وهذا طبعا ما أقوم به الحمد لله شكر الله، أنني لا أعمل تجارب لكن أستعين بتجارب الآخرين لكي يطور نظريتي بسبب أن الفضاء موحد. أي تجربة هنا ولا هناك يجب أن تكون موحدة مع نظريتي، خصوصا أن التجارب كلها تقام على فضاء الأرض، ففضاء الأرض يعتبر فضاء موحد. لكن إذا هناك تجربة قيمت على فلنفترض داخل الشمس أو داخل ثقب أسود، وأردت أن أقارن نظريتي بها، فستكون هناك إشكالية، ويعني تعالج هذه الإشكالية. طبعا نظرية تستطيع أن تعالج هذه الإشكالية لأن نظريتي تتحدث عن كوانتم جرافيتي، لكن دعنا نقول أن ميكانيك الكم، فميكانيك الكم داخل الشمس تختلف تماما عن ميكانيك الكم على سطح الأرض، وميكانيك الكم داخل الثقب الأسود تختلف تماما عن سطح الأرض. لهذا يعني ستكون هناك إشكالية، لكن إذا أدخلنا الدالة الأسية سنرجع إلى الأصل ونعرف أن الفضاء موحد والفضاء هو متصل في جميع الأنحاء، بالتالي نستطيع أن نعمل تجارب في أي مكان في العالم ونقارنها على سطح الأرض.
Between observables could be finite if E and M are eliminated. Okay. At least it's a logical possibility, right? Even if all those relationships here are divergent, it can be that the relationships between the observables, eliminating the left part of the picture, could be finite. And that is, of course, actually the case. But that is a non-trivial statement. It's not obvious. I do not claim it's obvious, but it's a logical possibility which is actually correct. And that is the idea of renormalization theory, to implement this program and in the end, of course, to prove that the hope is true. But first of all, we have to realize that it is not a problem for a theory if those formal parameters here, which are not observables, if they are divergent in such a limit epsilon going to 0. The only thing which matters for the predictivity and the sensibleness of the theory is that the relationships between observables, that must of course be finite. And that must be in agreement with such physical postulates as discussed before. So, if we have this hope, we can use this kind of practical procedure, is that we say, I will write it once again, E and M is now a function of, for example, sigma 1 and sigma 2. So it looks like this. We measure sigma 1 and sigma 2, then we obtain these now so-called bare parameters as a divergent function of those. Once we have it, we predict all the other observables and the result will be finite. Now, that is the principal idea, which is actually also possible to apply really like that in practice. It's not a bad thing to do exactly this. But there is often a technical simplification which I now also explain. Namely, it is sometimes awkward to express really observables as a function of other observables. Observables are kind of quite complicated objects, and it's easier to express all the formulas in terms of not observables but of simpler quantities like E and M, but E and M are unphysical Baire parameters, and so therefore what is now often possible, let me do it in another color, we can of course introduce new finite parameters. Let's call it E renormalized and M renormalized, for example, as fixed functions or with fixed and finite relationship to two observables, for example, to sigma 1 and sigma 2. So we just replace sigma 1 and sigma 2 by two new quantities with a fixed relationship which is by construction finite. And then instead of expressing everything in terms of sigma 1 and sigma 2, we can now express everything as function of E renormalized and M renormalized, and it still will remain completely finite. Therefore we can say here, or as function of E renormalized and M renormalized. And then it is typically possible to choose those so-called renormalized parameters such that their role is kind of what the name suggests. Their role is something like a charge and a mass. However, this charge and this mass do not have divergent relationships to observables, but by definition they are finite relationships to observables, and therefore those renormalized quantities, they are not the same as those original Baire quantities which are in the Lagrangian, but they have also some calculable and probably divergent relationship. But ultimately what we can do and what we want to do is to express all observable quantities as a function of two finite quantities, and we can choose either two observables, that is maybe the most the simplest thing to think about, or in terms of two new so-called renormalized parameters. That is the general idea, and the fact that it works is, as I said, not obvious at all. That is proven by complicated theorems, which you can find in particular in the other lectures, which are on video also. But it can be applied in practice, and today we will do that program explicitly for the photon vacuum polarization, and you see that at least there it works. And then you can understand what is the principle, and the generalization is then done for other opportunities. Okay, so that is our plan, and therefore with this in mind, let us try to do it concretely. Do you have any questions to this outline? Yep. We will, of course, look at concrete examples, because the vacuum polarization will provide an example, and then for all of what I say here, there will be explicit formulas. But in principle, what it will look like is that, for example, sigma 1 might look like this. E square plus e to the fourth power times 1 over epsilon. Something like that. This is how such a divergent formula can look like. And then you could, on the other hand, say, by definition, sigma 1 is equal to E renormalized square. And then you have also a finite relationship by construction between this divergent relationship between E renormalized and this original E square, which is now called Baire. And then you simply say, I assume that sigma 1 is finite, E renormalized is finite, and I can now calculate that their their charge is divergent because of this relationship. And then maybe you calculate the second observable. What could it be? For example, if you calculate, it is maybe this E bar square plus e to the 4 bar times 1 over epsilon plus e bar square 4 to the 4th times q square. Okay, so the second observable is different from the first one, but you see that the second observable differs from the first one by a finite amount only, so you could express sigma 2 as a function of sigma 1 and the result would be finite, or you could express it as a function of this renormalized charge and then the result would be finite as well. So this is kind of the structure in a nutshell that will emerge. Other questions? Yeah, so we will look at exactly those formulas after doing the calculation. And the photon vacuum polarization is basically the quantity which gives rise to such results here. And there will be a certain property of the vacuum polarization which will tell you why it's actually possible that all observables become finite simultaneously. There is a certain structural reason and a certain structural property in the vacuum polarization and in the way these divergences appear, which allows the simultaneous finiteness of everything. Because that is, of course, non-trivial. Basically, you have two parameters to absorb the divergences, but infinitely many observables. So you have infinitely many relationships, all of which must become finite by just absorbing divergences in two quantities. And that is a non-trivial thing to do, and it works because of certain properties of the vacuum polarization. So, okay, let's begin, and then we can, let's say, do the same discussion once again after we have seen the results, and then it's maybe worthwhile to really discuss it once more. So, we will not immediately begin with the photon vacuum polarization, but we will do a little bit of general theory of so-called dimensional regularization, which is the regularization method that we will use here for our lecture and for the calculation. And so, let's say for half an hour or so, we will introduce basic concepts and sample calculations in that scheme, and then we are ready to apply it to the photon case and to calculate the vacuum polarization. The basic idea of dimensional regularization is simply this, namely, instead of calculating the integrals over loop momenta in 4 dimensions with this integration method, we have a d-dimensional space, and we assume d to be a continuous variable. So we have here a d-dimensional measure now, and we assume all of our momenta and other similar quantities to be d-dimensional quantities. And in order to make the dimension the same as the actual physical dimension, we introduce here a new prefactor where this mu is an artificial mass scale. And then you have here a mass parameter to the power 4 minus d times the d-dimensional momentum integration, so the dimension overall is 4, like in 4 dimensions. So, and we simply say all 4-dimensional quantities, like momenta, position vectors, also gamma matrices, and so on, they are now d-dimensional with obvious relationships. So, and then we want to calculate now immediately a basic integral in d dimensions. This will give us our master formula, which is all we need. Basic one-loop integral. And the integration which follows can be done in an integer number of dimensions. It's a mathematically correct calculation that we are going to do. But the result will be interpreted in d dimensions, where d is a continuous variable, which might be real or complex. And then, of course, for real or complex d, the result will be a definition. And by the calculation, it will agree with normal integrals for integer dimensions whenever the integral converges, but the result will be defined also for complex d, and then you can take limits and expand in d minus 4. That is the point. And so this gives rise to the simplest calculations of all the possible regularization methods which exist. So the integral that we are considering is this mu to the 4 minus d times a d-dimensional integral times the following. In the numerator we have a normalization n minus 1 factorial, and in the denominator we have k square minus q plus I epsilon to the power n. So we have here n and here n minus 1 factorial. That is a useful normalization. And this I epsilon is bigger than 0 and small. That is the I epsilon, which is the same as what comes in these propagator Feynman rules, but so far we have ignored the I epsilon in the propagator Feynman rules because at tree level that is not important. However, now in the loop integrations, that plus I epsilon is actually important, and we will read it in the next minute. And this
طبعا
here is assumed.
طبعا هذه المعادلة هي التي بنيت عليها في سلسلة السابقة نظرية المجال الكمي الفعال. بنيت عليها فرضية إن المقام يجب أن يكون أعلى من البسط، والحمد لله يعني السلسلة كاملة أكدت على الفرضية هذه، ولهذا بسببها اضطررت إلى أن أدرس فايمر رولز اللي هو مخططات فايمن بشيء من التفصيل، وهذا ما قادني لهذه السلسلة، لأنه هنالك شيء خفي جدا في موضوع هذه الدالة الغريبة وهذه المعادلة الغريبة التي يجب أن تكون المقام أعلى من البسط. لماذا تكون المقام أعلى من البسط؟ حتى تعطينا قيم متناقصة، تعطينا قيم متناقصة. هذا التناقص هو ضد الجاذبية، يعمل على ضد الجاذبية وضد البلوينج اب اللي هو الدايفرجنت، وهذا ما يفعله الفضاء صناعي الابعاد. الفضاء صناعي الابعاد يمنع كل دايفرجنت يحصل، بالرغم من أنه داخله في دايفرجنت، لأنه القوى الأساسية الثلاث لا تعمل أو تضمحل، لكن في النهاية هو يمنع ذلك. الجاذبية أيضا تفعل ذلك، تجعل القوى الأساسية الثلاثة تضمحل، لكن هو يحاول أن يمنع ذلك. فنحن على سطح الأرض نعيش في فضاء ثنائي الأبعاد، هو فضاء رباعي الأبعاد، لكن يتحكم فيه فضاء ثنائي الأبعاد، لأنه في الفضاء ثنائي الأبعاد هناك أشياء لا يمكن أن تصل إلى لا نهاية. السرعة لا يمكن أن تصل إلى نهاية، الجاذبية يمكن أن توصل السرعة إلى نهاية بالمناسبة، ليست لديها مانع. يعني اعتبر أن جاذبية الأرض ضخمة جدا، وأنت أو أسقطت جسما على جاذبية الأرض، سيكون هناك سرعات لا حدودية لهذه الجاذبية، لهذه السرعة للجسم الساقط على سطح الأرض. فالجاذبية لا تمنع ذلك، لكن ما يمنع هو الفضاء ثنائي الأبعاد. وما يمنع ذلك هو يمنع تأثير القوى الثلاثة حتى الأربعة أن تعمل في هذا الفضاء، وأن السرعات لا تصل إلى نهاية، لأن السرعة إذا وصلت إلى لا نهاية إذا الطاقة تصل إلى ما لا نهاية، إذا الكتلة تصل إلى ما لا نهاية، وهذه بالنسبة له إشكالية كبيرة جدا. لهذا نجد أن الفضاء ثنائي الأبعاد هو من يحقق الفيزياء الكلاسيكية على سطح الأرض، ونحن نعيش في فضاء ثنائي الأبعاد، أو على الأقل فضاء رباعي الأبعاد لكن يتحكم فيه فضاء ثنائي الأبعاد. كل كتلة لا تبلغ كتلة الثقب الأسود فهي يتحكم فيها الفضاء ثنائي الأبعاد. الثقب الأسود داخل الثقب الأسود لا يستطيع الفضاء ثنائي الأبعاد أن يتحكم في الأمر، وإنما ما يتحكم فيه هو كتلة الثقب الأسود. لهذا نجد أن في هذه المحاضرة، في هذه المعادلة، أن المقام لابد أن يكون أكبر من البسط. وعندما ذهبت إلى هذه السلسلة الآن نحن بصدد هذه، وجدت أن معادلة فايمان لا تعتمد هذه الآلية باعتماد كلي، لكن تعتمد على شيء آخر تسمى الكونتراكشنز. أيضا في نظرية المجال الكمي الفعال هناك كونتراكشنز كثيرة جدا، لكن هنا في فايمان هناك كونتراكشنز كثيرة جدا جدا، مما تجعل الكتلة وتأثير الكتلة والطاقة والموجة وكثافة الطاقة تجعلها محدودة، لا يمكن أن تصل إلى نهاية. لهذا نجد أن معادلات فايمان يعني تطبق طبعا هي بتعتمد على البرتبيشن ثيوري، فتطبق مثلا في التري ليفل والون لوب، تو لوب، أظن 3 لوب تكون هناك إشكالية حقيقة، أو الفورس لوب مثلا تكون هناك إشكالية، ف لا يستطيع أن يحل. وهذا الغريب أنه هذا ما يفعله الفضاء ثنائي الأبعاد. يعني الفضاء ثنائي الأبعاد عندما تطبق على 4 لوب شيء واحد سيفعله لك، وهو سيضمن لك أن الطاقة لا تصل إلى النهاية. يعني الطاقة لا تصل إلى النهاية، يعني الكتل ستكون بأي طريقة أو بأخرى ستكون ضعيفة جدا، ستكون كتلة ضعيفة جدا، وستكون كتلة صغيرة جدا مقابل الأبعاد التي نحن فيها. يعني يمكن تصل الكتلة عند 5 لوب أو 100 لوب، ممكن تصل الكتلة إلى 10 ناقص نقول 100. تخيل كتلة 10 ناقص 100 كيلو جرام، كيف تأثر على الفضاء؟ لا شيء. كتلة الفوتون حسب ما حسبتها أنا 10 ناقص 48 كيلو جرام. إذا قسمت على سرعة الضوء تربيع حتى نحسب الطاقة، أو ضربتها بسرعة الضوء تربيع 48 و 35، 10 ناقص 35، هذه هي الطاقة. طاقة النيوترينو 10 ناقص 5، طاقة الفوتون 10 ناقص 35. مع صغر هذا الكتلة صغرها الشديد، لكن الفوتون يتفاعل كهرومغناطيسيا أقوى من النيوترينو، فهذا شيء غريب جدا. لهذا انتقلت إلى أن تفاعلات الفوتون لا يمكن أن تكون بالكتلة، وإنما تكون بالشحنة، وهذه الشحنة تكون تعمل في الفوتون بطريقة مغايرة ما تعمل فيه في بقية الجسيمات، وهذا ما يعطي الفوتون خاصية أساسية أو تفرد، يكون جسيم فريدا. ربما الطاقة التي حسبتها أو الكتلة التي حسبتها الفوتون هي بسيطة جدا، يعني 10 ناقص 48 بسيطة جدا، لكنها حتما أقل من النيوترينو الذي هو الأوسيليشن له، اللي هو التغير فقط في الطاقة، هي 10 ناقص 5. التغير في الكتلة 10 ناقص 5، لكن كتلته لم يستطيع حسابها حتى الآن نسبة لقلة تفاعله مع المادة. النيوترينو لديه كتلة، والكتلة لا تتفاعل كتلة متعادلة، وبالتالي القوى الكهرومغناطيسية لا تعمل فيه. الفوتون يقال أنه ليس لديه الكتلة، لكن القوى الكهرومغناطيسية تعمل فيه عمايل كثيرة جدا. فهذا شيء تناقض رهيب وجميل يعني في الفيزياء، ويعتبر معضلة أو لغز في الفيزياء سأحاول الوصول إليه إن شاء الله.
To be positive for the moment. And we also will assume that the n here is big enough such that the integrals will converge. And for all the other cases where n is not big enough and where q is negative, the integral will be defined by analytical continuation in the complex plane. So, let us begin by singling out the K0 integral, in other words the integral over the energy component, because the problem is we have here Minkowski metric. Minkowski metric treats the energy differently from the spatial momenta, and therefore we do first the integral over energy alone, and then we treat the rest in a uniform manner. So the K0 integral. The K0 integral, you see here, we have a denominator, and the denominator can go to 0. It can happen if you do the integral over K0, that somehow there is a cancellation between K0 square and all the rest. And if there is a cancellation, the denominator goes to 0, and the plus I epsilon prescription comes into play, and we can calculate integrals over such denominators with poles nicely in the complex plane. So we look at the K0 integral as a complex integral, and then we need to ask what are the poles of the denominator in this integration variable K0. And the poles are obvious because you have here K0 square minus K vector square minus Q. So the poles are at K0 square equal to K vector square plus Q minus I epsilon. So let's draw the complex plane. Here is the complex K0 plane. Here is the real part of K0. Here is the imaginary part of K0. And let's draw into the complex plane the location of the two poles of the integral. Where are the poles? The poles are at Q square, K0 square equal a positive real number minus I epsilon, where epsilon is a very small positive number as well. So the pole, one pole is at a square root of this, which is a number with a positive real part and a very small negative imaginary part. So one pole is here, below the real axis. And the other pole is at the negative of this, so it's here, just above the real axis at negative real parts. These are the two poles of the integrand in the complex K0 plane. Now what is our integration contour? Our integration contour is the real axis. We integrate over K0 from minus infinity to plus infinity, so we integrate over the real axis. So that is our integration contour. So that is our integration contour. Let's call it integration path 1. Now what can we do in the complex plane? You know residue theorem, I hope. And the residue theorem tells you that it's easy to evaluate complex integrals over a closed contour in the complex plane, because then you only have to look at the poles and their residues. And so let us now look at the following path in the complex plane. We take this, and we don't go to infinity, but we stop here. Then we take here a part of a circle, go here to the imaginary axis, then we go back along the imaginary axis backwards, then we take here again a circle, quarter of a circle, and go towards the real axis. And now we have a closed contour of integration paths in the complex plane. Let's call this here path 2, the negative imaginary axis, and then we have two circles here. It's in path 3 and path 4. Then how have I chosen the complex path? I've chosen the path such that there are no poles inside of the path. The path does not encircle any of the poles. And therefore the residue theorem tells us if we do the integral in the complex K0 plane over this blue path, the integral will be zero. And that can be used. So let's write it down. The residue theorem tells us that the integral over K0 over path 1 plus integral K0 path 2 plus integral path 3 and 4 of our integrand, of course, that sum vanishes. But we know also more, namely, so this path here is now doesn't go to infinity, but it's kind of at a fixed radius here. But let us make the radius of these circles bigger and bigger. Then of course here we converge towards an integral over the real axis. Here we converge towards an integral over the imaginary axis, and the circles get bigger and bigger. What happens to the integral over these circles? The integral over the circles has something where in the denominator here there is K0 on the circles, where the absolute value of K0 is as big as the radius of the circle that we have chosen. So the integral behaves like 1 over the radius square to the power n. If n is sufficiently large, then that integral over the circles will go to 0 if the radius goes to infinity. So therefore we can neglect this. That goes to 0 if the radius goes to infinity. And simultaneously, if the radius goes to infinity, that will just be our original integral over the real axis, and that will be an integral over the imaginary axis, and then we get a relationship that our original integral is minus the integral over the negative imaginary axis. And that is a relationship that we can use. So therefore, we obtain the integral from minus infinity to plus infinity of dk0 of our integrand is the same as the integral over the negative imaginary axis. So it's from minus I infinity to plus I infinity of dk0 with the same integrand. And now we can go on and do an integral variable substitution. We simply say, okay, we introduce a new variable which we call Ke, for E stands for Euclidean, then we get Euclidean metric. So we say I times Ke0 is equal to our original Minkowski K0. And then we can replace this here by an integral over I times dke0 with the appropriate integrand. And what are the integration limits? So if k0 goes from I infinity and E times ke is equal to k0, then ke0 just goes from minus infinity to plus infinity. So this new variable Ke, the Euclidean energy basically, is now a real integration variable, and we got a factor of I from the substitution. And the whole thing, which we have now proven to be possible, is called Wick rotation. And in total, it gives rise to the following relationship. So let's introduce a new symbol. So our original Minkowski K square is of course this K0 square minus K vector square. This is now the same as minus the Euclidean energy square minus K vector square. And so here we now have something completely negative. We can write this as minus Euclidean vector square. So that is the definition. So Ke square is now a two-dimensional Euclidean vector. And this KE square is simply the energy KE0 square plus K vector square. So we have now a d-dimensional Euclidean metric instead of d-dimensional Minkowski metric. And we have shown the following to be true, namely our original integral can be written as follows: I times mu to the power 4 minus d times now the d-dimensional Euclidean integral over the variable d-dimensional Ke divided by 2 pi to the power d, then n minus 1 factorial divided by, here we simply have minus Ke square minus q plus I epsilon to the power n. So, and here we have now a Euclidean d-dimensional integral and a Euclidean d-dimensional variable Ke square. And so now the denominator here is negative definite. So q is positive, Ke square is positive definite. Therefore, the denominator never goes to 0 in the integration region. It doesn't even approach 0, it doesn't even come close to being 0. Therefore, this epsilon, which is very small, can now be neglected. It doesn't matter anymore. The integrand here in the bracket is always more negative than minus q. Now, negligible. It has done its purpose of telling us where the poles are, and because of the location of the poles, this particular contour is the correct one to choose, and therefore we get a certain sign here in the prefactor of this substitution rule. That it
طبعا هنا هناك قضية لاحظتها، هو أنه ذكر أنه نجعل الراديوس أو نصف القطر للمحاور كالدائرة اللي هو نصف دائرة في المحاور الكارتيزية تذهب إلى ما لا نهاية. إذا ذهبت إلى ما لا نهاية فماذا يعني هذا؟ يعني أنه سيطرة الفضاء ثنائي الأبعاد. لماذا؟ نحن نرى الكواكب مجموعة شمسية أو نعم نرى كواكب مجموعة شمسية، نرى أن تأثير الشمس على عطارد كبيرة جدا، يعني ممكن يحسب بالنسبية العامة. تأثير الشمس على الأرض قليل، تأثير الشمس على بقية الكواكب قليلة جدا، وهذا واضح في قانون كيبلر، حيث أنه أو حسب كتاب حلقة 41 42 43 أنه كلما بعدنا عن الكتلة نشاهد الكتلة أضعف، هذا ما نراه في البروتون 10 ثانية 28، لأنه نحن بعيدين منه، لكن إذا جينا قريبين منه سنراها كتلة كبيرة. فإذا عندما تذهب إلى ما لا نهاية، نصف القطر يذهب إلى ما لا نهاية، فهذا يعني يجعل تدخل في سيطرة الفضاء ثنائي الأبعاد. وكما ذكرت أن الفضاء ثنائي الأبعاد يميل إلى الأشياء تتحرك بسهولة ويسر ولا تصل إلى قيم نهائية مثل الفيزياء الكلاسيكية. فبالتالي السبب الأساسي الذي جعلنا يعني يعتمد فكرة أن نظرية المجال الكمي الفعال تطيع نظرية علي يوسف هي هذا السبب. طبعا لم أذكره في السلسلة السابقة لكن اكتشفته الآن. الفضاء ثنائي الأبعاد لديه خاصية أخرى، أنه يجعل القوى الأساسية لا تعمل، وهذا واضح لأنه حصلت إذا أصبحت القوى الأساسية تعمل يعني هناك انتراكشن، يعني هنالك كيرفيتشر في الفضاء، هذا الكيرفيتشر يعمل على تقوية الكتلة والجاذبية، والفضاء ثنائي الأبعاد لا يريد أي من هذه أن يحصل. بالتالي سيطرة إذا جعلنا نصف القطر يذهب إلى ما لا نهاية، هنا ستظهر إشكالية. هو ليست إشكالية لأنه يعبر عنه ب كوبلين كونستانت. هذه الأمر يعبر عنه كوبلين كونستانت، حيث أنه الكوبلين كونستانت يصغر كلما ذهبنا إلى الترمس الأعلى في المعادلات. كل مرة الدرجة الأولى، الدرجة الثانية، الدرجة الثالثة، نجد أن الكوبلنج كونستانت يصغر. يعني مثلا الكوبلنج كونستانت الجاذبية أقل من كوبلنج كونستانت للكهرومغناطيسية، يعني أقل من ألفا اللي هو 1 على 137. فهذا يدخل في سيطرة الفضاء ثنائي الأبعاد. لكن في الحقيقة أن الجاذبية تحت الأبعاد الصغيرة جدا تعمل عمايل أكثر من الكهرومغناطيسية، ولهذا نجد أن الفضاء ثنائي الأبعاد هو يحارب الجاذبية أكثر من الكهرومغناطيسية، ولهذا تظهر خصائص الكهرومغناطيسية بالنسبة لنا أكثر مما تظهر خصائص الجاذبية. بهذا السبب يعني، لهذا السبب.
The outcome of the epsilon. So then, now we have an integral in d dimensions, which depends only on k. Depends only on ke square. So this is a spherically symmetric integral over just a spherically symmetric coordinate, and therefore we can evaluate it in spherical coordinates, polar coordinates in d dimensions, and then we have actually completely standard mathematical integrals. So we now have really standard integrals, and we can evaluate them in spherical coordinates. And you have an exercise where I assume that you can check all the integrals which now come. And so actually the result is then simply the following. Our I is I times mu to the power 4 minus d times. So spherical coordinates which are completely symmetric, we get a factor of the d-dimensional surface of the d-dimensional unit sphere. We can integrate over all the angles immediately, since the integrand doesn't depend on the angles, omega d, divided by 2 pi to the power d from here. And then we only have the radial integral, and it's 3 factors, n factorial, n minus 1 factorial, and then we can also factor out minus 1 to the power n. And then what remains is only the spherical, the radial integral, let's call it kappa, d kappa, over kappa to the power d minus 1 from spherical coordinates, divided by the integrand kappa square plus q to the power n. So kappa is the radial coordinate. So and then that is your exercise. You can calculate the surface of the d-dimensional unit sphere. The result is the following: 2 times pi to the power d over 2 divided by the gamma function, gamma with the argument d over 2. That is your exercise. It's not difficult once you know what the definition of the gamma function actually is. That is basically a very direct calculation. And similarly here, this integral is also a standard mathematical integral, one-dimensional integral, which can be related to the definition of the so-called beta function. The beta function is related to the gamma function, and this integral can then be expressed as follows: 1/2 q to the power d over 2 minus n times the following combination of gammas: gamma of d over 2 times gamma of n minus d over 2 divided by gamma of n. So and then we have everything. We can write down our final result for our standard integral I. And the result actually simplifies a lot, because here from the surface of the unit sphere we have gamma of d over 2 in the denominator. From the beta function we have gamma of d over 2 in the numerator, so they cancel. Then gamma of n is nothing but n minus 1 factorial, so the 2 also cancel, which is the reason why I put this normalization in the beginning. And then what remains is just the 2 pi to the power d. Here pi to the power d over 2, so that must be combined somehow. And the 1/2 and 2 also cancels, and then what remains is the q to this particular power. So not much remains, so let's write it all down. We have the I. The I came from big rotation, minus 1 to the power n, that doesn't go away. Then q to the power d over 2 minus n times 4 pi to the power minus d over 2 times gamma function of n minus d over 2. And this 4 pi comes from combining the pi to that power times the pi with the other power. And this is the nicest way you can write it. So that's actually a very compact result. It contains our physical variable q. Q is the only physical quantity in the integral, which the result must of course depend on. It contains this q to a certain power in a power-like quantity. And actually you could have guessed this power behavior from the very beginning, because actually the u is missing. U to the power 4 minus d. That of course just remains unchanged. But the q comes just from dimensional analysis. You can look at the unit of the result, and the only dimensionful quantity is q. Therefore q must appear to that power in order to match the unit of the left-hand side of the equation. Now we can use the, let's say, idea of dimensional regularization, where we set the dimension to 4 minus 2 epsilon, and epsilon is then our regularization parameter. And from now on, we allow that the dimension is actually an arbitrary real or complex number. And this epsilon might also be an arbitrary real or complex number. In particular, it can continuously go to 0. And the integral is now here defined for arbitrary values of d. It's an analytic function. It's a holomorphic function of d. So it's well defined in the complex plane. Initially, it's only defined in a certain region for positive q and for sufficiently large n. But now everything here is analytic holomorphic, so you can use analytic continuation to define it for all q and so on. And by the way, I use a different notation for this epsilon and the other epsilon. If you want, you can copy my notation. So this is in LaTeX, the var epsilon. And that here is in LaTeX, the epsilon. So just to let you know that I always distinguish that epsilon, which is small positive and has to do with the propagators and complex poles. That here is our regularization parameter, and the two have absolutely nothing to do with each other. So if we plug that in, then we can write down our integral once more, and we can first summarize all the factors which we get if we plug in d exactly equal to 4, ignoring the epsilon for a moment. So what happens if we set d equal to 4? Then we get the following factors. We get 4 pi to the power minus 2, and we get the I, so we can have the prefactor I over 16 pi square. Then the mu doesn't appear for d equal 4, and here we get q to the power of 2 minus n. And of course we also have the minus 1 to the power n. Then we get the correction for the d equal minus 2 epsilon. So here from the mu, we get mu to the power plus 2 epsilon. From here we get an additional q to the power minus epsilon. So overall we get the ratio u squared divided by q to the power epsilon. And then we get the gamma function. And from the 4 pi we also get 4 pi to the power epsilon, and the gamma function of n minus, 2 plus epsilon. That is our final result, separated according to things in 4 dimensions and quantities which explicitly depend on epsilon. So for epsilon going to 0, that might go to some value, maybe to 1 over epsilon. Anyway, let me stress again that this behavior here and also that behavior here, that could be predicted. So that is, let's say, clear from dimensional analysis. This here is coming out of the calculation, so that cannot be predicted from dimensional analysis, but it's a result of the calculation, and it's interesting because from the loop calculation we apparently get some small prefactor. 1 over 16 pi square is a number which is less than 1%. So therefore typically the results from one loop calculations are suppressed by this factor which is less than 1%, and so the one loop corrections are typically small. So this is a typical one loop prefactor, which will appear in all one loop calculations. And then here, that is also the result from the calculation. So this non-trivial part of the result, which must come from the explicit calculation, that is this gamma function. So the result depends on our regularization parameter epsilon, mainly in terms of this gamma function here, which is a known mathematical function, and therefore it's very easy to analyze and to plug in results into explicit computations. So that ends our discussion of the so-called master formula. This is the master formula. We started with a very simple, however also quite general one-loop type diagram, namely a d-dimensional k integration over something which looks like a propagator with some arbitrary quantity here, but otherwise it looks like a propagator with a momentum k square to some power. And as we will see in a moment, all one-loop integrals, okay, we will see it for one example, but I can tell you that all one-loop integrals in quantum field theory can be reduced to this expression. Therefore, this expression is actually enough to evaluate all one-loop integrals that can appear in any quantum field theory like QED. How that works, I will show you. Okay? But therefore, the master formula is very important, and it gives rise to this one-line result, which is a function of epsilon, where epsilon can be defined in the complex plane. By the way, it's not important that the dimensional regularization epsilon can be complex, but what is important is that all these functions here are analytic functions. Therefore, we know a lot about their behavior, like Taylor expansions, continuity, differentiability, and so on. And we also know that they can be analytically continued from some region where integrals converge to other regions. Next step. We slowly move closer towards our vacuum polarization. And we compute one specific loop function which has a name in the literature. It is called B0 of 0, m, m. This loop function is defined as follows. Namely, we define this one loop prefactor I over 16 pi square times B0 of 0, m. That, and so the B0 will then be the interesting part without this typical one loop prefactor. Okay, that is why the definition is like that. And it corresponds basically to this Feynman diagram, where we have here no incoming momentum, so the incoming momentum Q is 0. Therefore, in both propagators, we simply have loop momentum K, and we assume that both propagators have the same mass m. And therefore, you can understand what the arguments mean. In principle, there would be a Q argument here if you have an incoming momentum Q, and if you have different masses, then you could have m1, m2 as arguments. And we only compute a special case where we have no incoming momentum and where both masses are equal to the same m. That is all we need, actually. But you can understand that there would be a more general definition. And so this particular case has then the following integral, namely mu to the 4 minus d times this d-dimensional k integral times 1 divided by k square minus m square to the power 2. So both propagators have the same mass m and the same momentum k, and therefore that is our integral. And this integral here is defined to be b0 with that argument times the 1 loop prefactorial. So, and you see that this integral corresponds to our master formula, right? It directly corresponds to our master formula. Namely, we have here n equal 2, we have the propagator to the power 2, and the general quantity Q is now simply m squared. Okay. So, and therefore we can immediately read off what the result is. What is the result for our B0 of 0, m? It's what we have here, apart from the factor I over 16 pi square. So what is it? That result. So minus 1 to the power 2 is now plus 1. Q to the power 2 minus n. N is 2. That is also absent. It's just 1. Therefore, we only get the epsilon part. We get mu square divided by m square to the power epsilon times 4 pi to the power epsilon times the following gamma function. N is 2 gamma of epsilon. That's all. Very simple result. So we have calculated our first one-loop Feynman diagram, namely this one. This is the result in dimensional regularization. Now let us discuss the result a little bit, and in order to discuss it, we need to know something about the gamma function. That was your exercise to prepare some background knowledge on the gamma function, so let me just repeat the main points. The gamma function has the property of this recursion formula, z times gamma of z is equal to gamma of z plus 1 for any argument c in the complex plane. So the gamma function is a function defined in the complex plane. And therefore it's a generalization of the factorial function. And so in particular, let's also write it down. Gamma of n is equal to n minus 1 factorial for natural numbers n. Now, the gamma function is defined in the complex plane, so it is an analytic function in the complex plane. And what is particularly interesting is to look at its expansion around the point 1. So gamma of 1 is 1, and therefore the expansion around 1 starts with 1 plus epsilon times the derivative of gamma at the point 1 plus higher orders in epsilon, epsilon square. And so that derivative of the gamma function at 1 is of course fascinating, very important mathematical irrational number, which has a name, and this is the so-called Euler-Mascheroni constant. And so we have here minus epsilon times gamma e plus order epsilon square. So the derivative of the gamma function at 1 is actually negative. and it's called minus this Euler-Mascheroni constant gamma E. So gamma E is called the Euler-Mascheroni constant. And it has a numerical value of around 0.57 and so on. So it's of course a transcendental irrational number. So putting this together, we can obtain an expansion of gamma of epsilon. What is gamma of epsilon? Gamma of epsilon can now be obtained by taking the recursion formula and the expansion around 1. Namely, gamma of epsilon is the same as gamma 1 plus epsilon divided by epsilon, because that is just the recursion formula solved for gamma of epsilon. But now we can plug in our expansion of gamma of 1 plus epsilon, which starts at 1. So we now get 1 over epsilon, that is the divergence. And we get minus the Euler-Mascheroni constant plus higher orders in epsilon. And so here you now see how dimensional regularization regularizes divergences. If we approach dimension d going to 4, epsilon goes to 0 and we get a pole. That corresponds to the divergence of our original loop integrals. But if we keep d unequal to 4 or epsilon unequal to 0, we get here a finite result. And so we have very nicely and in a mathematically very transparent way isolated our divergences, and that makes the renormalization procedure where the divergences should cancel again very, very transparent and easy to work with. So what we then need is some combination like this, some quantity x to the power epsilon times this gamma of d, because that's exactly the form of our result here. So how can you work with this? X to the power epsilon is the same as e to the power epsilon times ln x. That's the same, times gamma of epsilon. And so that is now expanded 1 plus epsilon times ln x plus higher orders in epsilon. And this is 1 over epsilon minus gamma e plus higher orders in epsilon. And so therefore if you multiply, we get one term 1 over epsilon still. Then we get minus gamma e, and here we get 1 over epsilon times epsilon plus ln x plus higher orders in epsilon. So, and therefore we can now expand our B0 result and interpret it. B0 of 0, m is equal to the following. So this whole expression has now that form 1 over epsilon minus Euler-Mascheroni constant, then plus ln x, and ln x is the logarithm of that combination here, which can be split into the logarithm of that plus the logarithm of this. So let's first write plus ln 4 pi plus ln u squared over q. That is our result for the B0 function when we ignore higher order terms in epsilon. And now you see here something. We can interpret the result. Namely, physical quantities are all contained in, actually q is of course m squared. And in general it might be q. But the physical variable here is only the n. That is the only physical quantity the result depends on, and that is localized here in that logarithm, which contains the ratio of this artificial mass scale mu and the physical mass scale m. That is the physical result from our loop integration. And that will enter observable quantities in the end. But this combination here is all a regularization artifact. So first of all, the divergence 1 over epsilon, which is the purpose of the regularization, but also those quantities here, they are kind of artificially introduced from the way we defined this dimensional regularization. Could have been done differently, but they basically come from products of the 1 over epsilon from the gamma function with these d-dimensional spherical coordinates and so on. So this is just as unphysical as the 1 over epsilon. And therefore we can combine all of those three quantities into one, and that is very often done in practical calculation. So all of this is often called capital delta, which is a typical divergent combination. So it's not everything is divergent, but it's a divergent combination. And if we would say B0 and then take only the divergent part, then by this we would mean this entire combination, because those finite parts can be attributed to the divergence. And that here is the physical finite result. And for example, on your exercise sheet, you are once asked to isolate the divergent part or the finite part, and then I'm referring to this kind of split. So that all would be counted as divergent, that would be counted as finite. Any questions to this B0 function? Yep. Yeah, you are thinking of QED, and this is just a generic Feynman diagram which does not correspond to QED, but where the propagators have simply a 1 in the numerator and where the vertices also are defined to be 1. So in that sense, it's a more abstract Feynman diagram, but it illustrates the integral. And of course, in QED, we have a complicated numerator and so on, and we have vertex vectors, and therefore in QED, which is now the next topic, we need to work a little bit until we find that our vacuum polarization can be reduced to this integral. Good. Okay, so let us maybe only leave the B0 function, which is of course what we need. And then we can now compute the vacuum polarization. Okay. Now I have to concentrate a little bit, because of course the photon vacuum polarization is quite simple to calculate, but only if you have experience. I have now tried a bit to optimize the sequence of steps exactly in this way, that we absolutely minimize what we need to do. And so I need to follow extremely closely this outline here. So pi gamma in dimensional regularization. So that was what we had in the beginning. So minus I times sigma mu of Q contracted over the two Lorentz indices, which was the same, which was basically given by this Feynman diagram with this minus dq square times the integral over k of the following trace, gamma mu k slash plus m, gamma mu downstairs, q slash plus k slash plus m. And in the denominator we have k square minus m square and q plus k square minus m square. That is our integral. And so the numerator is not 1, and the denominator does not have the form of our previous master formula, where we just have one denominator squared, but we have now a product of two different denominators. So therefore we have two task to solve. We have to get rid of the numerator, and we have to bring the denominator into the form of our master formula. And in order to do that, we will apply two tricks in the perfect order, I hope. But both tricks that I am going to show you are extremely general tricks. So they are not only applicable here, but those two methods are really the key methods in order to evaluate all loop integrals, actually not even only one loop, but also integrals of higher order. But we will apply it in a very specific way to this integral. So first of all, in the numerator, we have now the following combination again. K slash sandwiched between gamma mu, and we had this combination already before, but now we need to evaluate it once again in d dimensions instead of in 4 dimensions. So in d dimensions, you can still do the anti-commutator trick from before. So we write this as minus the opposite order plus the anti-commutator, and from the opposite order we get then gamma mu contracted, which gives now d instead of 4, and from the other term we get a factor 2. So we get 2 minus d times k slash, and previously we had 2 minus 4 was minus 2 times k slash, and now we have 2 minus d times k slash. And everything else is kind of obvious, and then we evaluate our numerator. So we have a simple trace with up to 2 gamma matrices only, because the gamma mu's are now gone. So we have a trace is minus dq square times the trace of the following. We have 2 minus d times k slash, and then times the other k slash plus q slash, and then we have the mass terms plus d times m square. The m square term has some just gamma mu contracted, gives the dimension d. So, and this trace is trivial, so you get minus dq square times 4 times the following, namely 2 minus d times the scalar product k square plus k dot q, because the trace of 2 gamma matrices just gives the metric tensor, and plus d times m square. Then we have our numerator, and our numerator is now a set of scalar products. It doesn't contain gamma matrices anymore, but only momenta or constants. So it's still a complicated numerator which depends on our integration variable k. So therefore we cannot apply our master formula, which had a 1 in the numerator. But that is the result for our numerator at first. Now comes the first of these very famous and very general tricks that we need to apply. And the first trick is the following. So-called Feynman parameters. Namely, we write 1 over a product a times b as an integral 0 to 1 dx of a times 1 minus x plus b times x squared. That is Feynman's trick. Actually, also Schwinger apparently invented this, but it's called Feynman parameters. So if you integrate, this is a trivial rational function to integrate over x, then plugging in the 2 limits gives you 1 over a minus 1 over b, and bringing it to a common denominator gives you 1 over a times b, and the numerator just cancels from the integral. So that is trivial to show by just evaluating the integral. And so that can now be applied to simplify our denominator. Let's do that here. Our denominator of the Feynman diagram was a product of 2 different denominators, and with Feynman parameters we can make it into 1 denominator squared, which is similar to our master formula. So let's apply this idea to our denominator, and then we get an integral 0 to 1 dx, of the following something square, and in the bracket we now have the sum of the two denominators times 1 minus x or times x. That gives k square minus m square times 1 minus x plus q plus k square minus m square times x. Okay, let's simplify. Let's simplify. How many k square do we have in the denominator? How many k square? Yep. Yeah, right. And if we add the prefactors, 1 minus x plus x gives 1. Right, so we have exactly k square without any x dependence. That is generally true in Feynman parameters, which is one of the reasons why this is so powerful. It's really a simplification. So we just have k square. What else do we have? How many m square do we have? Right, m square times 1 minus x, so minus m square. What else do we have? We have k dot q, 2 times k dot q times x plus 2x k dot q, and we have q square times x. So, okay, that's what we have. That is now similar, more similar to our master formula, but it's not yet quite the master formula because we don't only have k square, but we also have q dot k. And we can get rid of that by doing a variable substitution, basically complete the square, and then do an appropriate variable substitution. And so let's do the following variable substitution. K goes to k minus x times q. That is our variable substitution. And then our denominator in terms of the new k is now changed. In terms of the new k, our denominator is equal to the integral 0 to 1 dx. And then what do we have? We have k square plus 2x k dot q. If we plug in this replacement, the linear term q dot k, it just cancels. It drops out between the two terms. Therefore, we have just a new k square. But then we also get the q square times x remains. But from here we then get an additional term which is not there. So we have to subtract minus x square times q square. And then the rest remains plus q square times x minus m square. And then we have our master formula denominator, namely k square plus something else. And that we can integrate using our master formula. And we can call all of this stuff here minus capital Q. And then we have our master formula. The point is that this capital Q does not depend on the integration momentum. It depends on x. So we still have a one-dimensional integral to do, which we maybe didn't foresee. That will be simple to integrate. But anyway, now we have the structure of our master formula in the denominator. And so here we have a definition of our key. Good. What happens to our numerator if we do the same variable substitution? Of course, the numerator must undergo the same variable substitution now. Taking it from before, it becomes minus eq square times 4 times the bracket. And what is going on in the bracket? 2 minus d times. Okay, now we have to calculate a little bit. K square plus q dot k. If we replace k by this combination, we get the following: k square plus x square q square minus x times q square plus terms proportional to q dot k plus e times m square. So here I give you the result, and I omit terms of the form q dot k let's not bother to write down what they are, but the k square terms and the q square terms, they are explicit. So, why do I not bother to write down the k dot q terms? Because they drop out. They would appear as follows: the integral over k with a numerator k dot q divided by k square minus q square in the denominator. So we have even odd integrand. So the numerator is odd in the integration variable, the denominator is even, and we integrate over all of space-time. Therefore the integral vanishes. Therefore we can only consider the even terms k square and the q square. So now we have to combine everything. Our full integral is now the integral over this numerator divided by that denominator. And that is still not simple because our master formula contains a constant in the numerator, and here we, however, have k squared. That is not a constant, so we need another simplification. And that simplification is again possible by doing a second extremely general and very important trick, which can be applied here in a specific way, namely the so-called integration by parts. That is actually extremely powerful also for multi-loop calculations. And here it works as follows. We write down 0 on the left-hand side, and on the right-hand side we have an integral over k in d dimensions over a total k derivative, dk mu. So this always vanishes in dimensional regularization, and we can now write the following: k mu divided by k square minus q to the power 1. Okay. What happens if we evaluate this? So that must be 0, that corresponds to integration by parts, or surface integrals are 0. So if we evaluate the derivative, we get two terms. Once, let's apply the derivative onto the numerator. K mu derivative with respect to k mu. For each component we get a 1, and we contract over all the components, so we get d, the number d of dimensionality of space-time in the numerator, divided by that denominator. Then from the other term we get we apply the derivative onto the denominator, so we get minus the denominator squared. And in the numerator, first of all, we get the k mu, but then we get the inner derivative 2k mu as well. Now you see here k squared divided by something squared, which is exactly the term that was disturbing us. So we get a relationship which relates our term, which we don't like, to something which has a constant in the numerator. But actually we can simplify it here a little bit more. Adapt it to our case, and as I said, I need to follow here very closely my notes. So let's bring it all to one structure with the denominator square, and then we can expand here d times k square minus q. So that is the same thing, minus 2k square. And then we have here another k square in the numerator, and we can write it as follows. We get the following consequence, namely on the left hand side we have 0, and on the right hand side we have d minus 2k square is equal to something. So let's write this as the following: integral 2 minus d times k square divided by the denominator square is equal to the rest, is equal to minus d times q divided by the denominator square. And so that is well adapted to our problem, because in our problem the k square actually appears with a prefactor 2 minus d. And now we can directly relate 2 minus d times k square to something else. And now we can write it down. So the integral numerator divided by denominator is now equal to the following: minus e times q square times 4 times the integral. And what is now our integral? We have the denominator k square minus q squared. And in the numerator, let's collect 2 minus d times k square has become minus d times q minus d times q. Then we get plus 2 minus d times this q square term, 2 minus d times x square minus x times q square plus d times x square. That's all. It fits here. Right. And so now magically it simplifies even more. So you see the k square has gone. It was replaced by that minus d times q from here. And the complicated q square messy term here, we see here, and d times m square appears there. So what was actually minus q? Minus q contains minus m square. So inside of this minus d times q, there is minus d times m square plus d times m square drops out. The m square completely drops out. Then what remains here in the minus q, what remains is just that. Minus x square q square plus x q square. That is the same structure as here. It's the same structure as here, but with a prefactor minus minus and minus 2 minus, so minus d. So therefore we get this term times 2 minus d minus another d gives that term times 2 minus 2d. That's all. So we get the following: minus e times q square times 4 now times 2 minus 2d times integral over x square q square minus x times q square divided by the propagator square. And now we have it here, we have our master formula, because now from the loop integration point of view, the numerator does not depend on k anymore, so it is a constant. The denominator has the master formula form k squared minus q square. So the result here is actually our b0 function with the argument q and some prefactor. And so let's write it down. Minus e times q square times 4 times 2 times 1 minus d. Let's write it like this. Then times x square minus x times q square times I divided by 16 pi square times b0 of 0, q, q. And so time is almost up, but let me just write down the final result for the vacuum polarization, because now we have completely evaluated it. So the left-hand side of what I wrote here was the vacuum polarization times a prefactor. The prefactor came from the contraction of the two indices mu mu. And the prefactor also contained exactly this. The prefactor contained 1 minus d and q square. So we can directly read off from this not only the self-energy sigma, but the vacuum polarization pi gamma. Yes? Yeah. Okay, that was always kind of included. Right, so let's put it here, integration over x. Yes. So then we can read off the full pi gamma by dividing by all the prefactors that we had collected before. And then the pi gamma is actually E times Q square divided by 16 pi square. That comes from the one loop prefactor. Then times 8 times the integral 0 to 1 dx of x minus x square times E0 of 0, q, where q is given by m square minus q square times x times 1 minus x. And for tomorrow, let us abbreviate the whole thing. Yet another name, a gamma of q square, where a gamma of q square is simply the same apart from the coupling constant, which we want to exhibit in order to do bare versus renormalized E and so on. And then it's nice to have here a combination a gamma, which depends only on integrals and not on coupling constants. So this is our result. And the B0 function was given explicitly. It contains a logarithm of q, and so what we end up with here is a one-dimensional integral over x over a logarithm of x's and q squareds and m. So it's a not completely trivial one-dimensional integral, but of course completely well-defined and could be evaluated numerically or analytically as you wish. That is our vacuum polarization, and we have computed it quite quickly by applying Feynman parameter and integration by parts, and in such a way that we could immediately divide by all the prefactors and get this nice integral representation. And tomorrow we will do physics with it, interpret it, see the finiteness of observables, and then discuss physics implications of this result here. Okay, so see you tomorrow.